In July 1966, the Commander-in-Chief, Pacific Air Force, informed the Chief of Staff, U.S. Air Force, of the critical munitions storage problem existing in Southeast Asia. The problem was caused by the shortage of land upon which bombs could be stored, and the fact that all munitions must be stored according to standard Department of Defense quantity distance criteria. These criteria required more land than was available on our Air Force bases in Southeast Asia. Under the direction of the Chief of the Explosive Safety Branch, Directorate of Aerospace Safety, a special Air Force ad hoc study group made an intensive 8-day probe. Assisted by consultants from the Armed Services Explosive Safety Board and the Army Ballistic Research Laboratory, the group developed and recommended new storage criteria that would increase the quantity of bombs that could be stored in a given area by 2.5 times. The Chief of Staff approved the study group's recommendations and directed that they be validated by testing. After a munitions safety assistance team reviewed combat zone storage areas in PACAF, a 4-phase test program was devised to validate the new criteria. This is the story of those tests. The Hill Air Force Base test range, just west of the Great Salt Lake, Utah, was selected for the full-scale field test nicknamed Big Papa. Construction of the Phase 1 test facility began on July 1st, 1967. Phase 1 was designed specifically to validate the revised quantity distance munitions storage criteria. The donor stack placed here consisted of M66 2,000-pound bombs and M117 750-pound bombs. Although the 2,000-pound bombs are obsolete, they were considered completely adequate for the purposes of these tests. All bombs were filled with Tritonol for a total of 250,000 pounds net weight of high explosives. They were primed to be detonated simultaneously. 5 acceptor bomb stacks were placed strategically around the donor. Acceptor A1 was the same size as the donor. All other acceptor stacks contained 75,000 pounds net weight of explosives. Standard earth barricades separated all acceptors from the donor. Stacks A1 and A3 were placed 70 feet from the donor. Distances between the donor and all acceptor stacks were computed from the standard quantity distance formula. Distance equals K times the cube root of the net weight of high explosives. The K factor is the key to this formula. Standard quantity distance criteria had established the K factor at 6 for this particular type of munitions storage. However, the study group's recommendations reduced the K factor to 1.1. Here, 70 feet represents a K factor of 1.1 for 250,000 pounds of high explosives. Stack A2 is closer to the donor. It was placed at a distance of 58 feet 6 inches, or a K factor of 0.9. Acceptor A4 was 158 feet from the donor, a K factor distance of 2.5. Acceptor A5 was placed 158 feet from acceptor A1, a potential donor. Stack A5 was placed on the ground. All other acceptors and the donor were on reinforced concrete pads. This then was the configuration of Big Papa, Phase 1. A 250,000-pound donor would be detonated, and its results on the acceptors would be observed. All references to weights refer only to the net weight of high explosives within the bomb, and do not include the weight of the bomb cases. It was decided early in the program that sufficient instrumentation should be used to measure all pertinent blast effects, both for immediate use and for future research of barricades and quantity-distance relationships. Electronic and mechanical air pressure gauges were placed at critical intervals out to 1 mile from ground zero. Velocity gauges and accelerometers were placed on the ground surface, in the earth berms, under the earth berms, and in the concrete storage pads. Transmission cables leading from the instruments had to be shock isolated by foam rubber and buried to protect them from blast effects and electromagnetic interference caused by shock waves. A completely automated instrumentation recording trailer was used to record data. It was designed by the Air Force Weapons Laboratory to be buried close to large detonations for this very purpose. Fragmentation survey areas 300 feet square were established at set distances from ground zero. These areas were graded and compacted so all fragments could be collected and analyzed. On July 26, Phase 1 of Big Papa was ready. All bombs of the 250,000-pound donor would be primed and detonated simultaneously. Phase 1. The blast was recorded in extreme slow motion since the actual time of the explosion was very short. The detonation of 250,000 pounds of high explosives. What happened to the bombs in the acceptor stacks? One acceptor was only 58.5 feet away from the donor. There was no sympathetic mass detonation of any of the acceptors. This stack was the most disarranged of all. It was the one which was on the ground rather than on a concrete pad. This stack was the least disarranged. As you can see, many of the bombs are relatively undisturbed and could be moved with the forklift for immediate use. Acceptors A1, A2, and A3 were all buried under several feet of debris and earth from the crater, but there were no mass detonations of any of these acceptors. Acceptors A1 and A3 were spaced, you will recall, at a K-factor distance of 1.1 from the donor. This was the K-factor distance recommended by the Special Study Group. Acceptor A2 was located at a K-factor distance of 0.9 from the donor, which further enhances the validity of the 1.1 K-factor. However, the bombs in these three acceptors were buried to the extent that considerable effort would be required to extricate them. Phase 2 of Big Papa was fired on August 30th. This test was essentially a repeat of Phase 1, but with only 3 acceptors. Again, 2 acceptors were placed at a K-factor distance of 1.1. One acceptor was placed at a K-factor distance of 0.8, only 50 feet from the donor. This made a total of 6 acceptors in the 2 phases, which were tested at K-factor distances of 1.1 or less. Just as in Phase 1, the donor, again containing 250,000 pounds of high explosives, was detonated. And again, no sympathetic simultaneous mass detonation occurred in any of the acceptors. This is the acceptor which was nearest to the donor. It was completely buried and disarranged, but none of its bombs was detonated. These results indicate that a K-factor separation distance of 1.1 is acceptable. Another result obtained from Phases 1 and 2 showed that the standard 2-degree rule on barricade height is effective and should be followed. The 2-degree rule requires that a line drawn from the top of the far side of a bomb stack at a minimum angle of 2 degrees above the horizontal must pass through the entire 3-foot-wide top of berm of the standard earth barricade. This height of barricade will minimize the possibility of fragments striking other bomb stacks with sufficient velocity to cause their detonation. High-speed fragments passing above such a barricade would not likely have sufficient striking velocity to cause detonation of another bomb stack. Phases 1 and 2 empirically validated the newly recommended quantity-distance criteria for munition storage, along with properly constructed standard earth barricades. So Phase 3 was executed in an attempt to determine if barricade materials and geometric configurations other than those used in the standard earth barricade could be used successfully. The donor in Phase 3 contained bombs totaling 100,000 pounds of explosives. Foamed concrete acceptors simulating the actual size of bomb stacks were used instead of real bomb stacks. This foamed concrete had been pre-tested so that the energy of any fragment embedded in it could be calculated. From this, it could be determined if that fragment would have detonated a bomb it might have struck. 6 different types of barricades were used in this test. The standard earth barricade, one barricade made of soil cement mixture, and 4 different metal bin-type barricades. Each of the metal bin-type barricades were erected and then filled with earth. No evidence of fragment penetration was found in the foam concrete simulated acceptors. This would indicate that all the barricades were effective in stopping the bomb fragments. However, the results of this phase of the test cannot be taken as conclusive. Due to unexpected groundwater conditions, the blast created a much larger crater than was expected. This demolished much of the foam concrete acceptors and made fragmentation data difficult to confirm. One result, however, was conclusive. The metal barricades created secondary fragments, particularly the heavy steel structures. Therefore, if metal barricades are used in bomb storage, they should be of the lightweight variety and of as few parts as possible. In the first 3 phases of Big Papa, all bombs in the donor stacks were detonated simultaneously to create the largest possible blast pressure and shock wave. But what would happen if only one bomb in a stack was detonated? Phase 4 was set up with a standard earth barricaded donor of 80 M117 750-pound bombs containing 31,000 pounds of Tritonol. 2 acceptors, each containing 39 2,000-pound Tritonol-filled M66 bombs, were used. It was speculated that if one bomb was detonated, other bombs in the stack might be hurled into the air and detonated, thus impinging fragments upon adjacent bomb stacks and causing their detonation. Test results did not confirm the speculation. When one bomb was detonated in the donor stack, all others also detonated simultaneously. There was no proof that any bombs were tossed into the air, and none of the acceptor stacks was detonated. The primary objective of the Big Papa test was to validate new high-explosive quantity-distance storage criteria recommended by the Air Force Special Study Group. The criteria were validated. Test results confirmed that bomb stacks containing as much as 250,000 pounds of Tritonol could be stored safely at K-factor distances of 1.1. The bombs would be buried and disarranged by a detonation, but there was very little likelihood of a sympathetic, simultaneous mass detonation. These criteria, of course, apply only when the standard earth barricade is used and properly constructed, and the bombs are stored in accordance with the 2-degree rule. Big Papa has shown that high explosive stockpiling does not have to take excessive amounts of valuable storage space. This diagram depicts the storage density permitted when using a K-factor separation distance of 6. as compared to this diagram depicting the increased storage density using the newly validated K-factor of 1.1. This empirical full-scale field test validated the new criteria for Air Force munitions stockpiling, and as a result, this storage configuration has been approved for use within the Air Force. It consists of 8 individually barricaded cells within one module. The K-factor distance between cells, each of which contains 250,000 pounds of explosives, is 1.1. So the Big Papa tests have validated the new criteria, which will not only permit greatly increased munition storage density, but also will result in the saving of millions of dollars in construction costs.